Hello and welcome, my name is Mahdi, and in this video we are going to dive into one of the most powerful features of modern C++, smart pointers. Before we get into what makes smart pointers so smart, let's start with a brief review of how memory is managed at runtime. When you run a program, the operating system gives it a dedicated block of runtime memory. But this memory isn't just one big unstructured space. It's carefully organized into different sections to store different types of data. Proper memory management is vital. It's important. It helps to prevent crashes and also helps to optimize system performance. In this slide, I am going to walk through the different segments of runtime memory using this simple code example. The first segment is the code segment. It's a read-only area that holds the program's compiled machine instructions. All executable statements go here. The next segment stores our global and static variables. They have a lifetime for the entire duration of the program. The stack segment is used for storing local variables and function call information. Note that the pointer variable, which contains a memory address, goes here, not the memory it points to. Finally, we get to the heap, where smart pointers come into play. In our example, it holds the value of 40, which is pointed to by the PTR pointer. With heap, programmers can request and release memory at runtime. It's useful when we don't really need a pre-allocated memory. This gives programmers a lot of power, but can also cause a lot of problems. Problems like memory leaks that I'll talk about it later. To truly understand the value of smart pointers and to describe how they help to develop safer codes, we first have to know why the heap can be so tricky to manage. Let's examine this with a simple program. At runtime, my function starts by asking the computer for a space in memory and store its address to a pointer. It is PTR here. Then it places the value 40 into that memory space. At line 15, the if statement checks a condition. Finally, at line 20, delete PTR releases the reserved memory back to the system. Pause the video and think, what is wrong with this simple program? What happens if the condition is true and my function returns 1 at line 16? What will happen to the allocated memory on the heap? This early return ends my function. It skips the delete statement at line 20. When the function ends, the pointer variable on the stack is destroyed, but the memory it points to on the heap is still occupied. And since you lost the pointer, you can no longer free it. That block of memory stays reserved until the whole application ends. This is called memory leak. In C++, when we allocate memory with new, we take on the responsibility of releasing it later with delete. This sounds simple, but in practice, it's very easy to miss. Even small leaks accumulate and can eventually bring down long-running applications. Let's see how smart pointers can help to make my function safer. You can see the same function written in two different ways. On the left, we are using a raw pointer, and on the right, we have updated it to use a smart pointer. First, we need to include the memory header to have access to the smart pointer library. Now look closely at line 12 in both versions. On the left, we create a raw pointer with the new statement. On the right, we create a smart pointer by using std double colon unique underline PTR. Both are pointing to a memory block on the heap, but the key difference is how the block is managed. In the raw pointer version, we must remember to call delete ptr to free that memory when we don't need it anymore. If we forget or if the function exits early, that memory is leaked. In contrast, with the smart pointers, we no longer need the delete statement. The system automatically takes care of releasing that memory when the pointer goes out of the scope. So, if an exception is thrown or the function returns early, the smart pointer still guarantees cleanup. This makes our code much safer and easier to maintain. Alright, let's switch over to some code and see smart pointers in action. I have written a very simple class here. The constructor just prints hello when an object is created, and its destructor prints goodbye when the object is destroyed. This way, we can clearly see when memory is allocated and when it is released. Let me collapse the class definition to save space. In the main function, I first use a raw pointer. We create an object on the heap, and at the end, we call delete to free that memory. If I compile and run this program, you will see exactly one hello and one goodbye message on screen. That's a pretty normal behavior. But what happens if I forget to call delete to release that memory? Let's try. So I make this disable, save, and run and compile. Okay. As you can see, this time there is no goodbye message on screen. This means the destructor never executed and we have a memory leak. In a small program like this, it's not a big deal, but in large, long-running application, it can become a serious problem, especially if memory leaks accumulate. Now let's fix it by switching to a smart pointer. This time, PTR is a smart pointer. Let me save and run it. Yep. Instead of a raw pointer, I used a smart pointer, and notice that no longer we needed a delete statement. And yeah, here we are. We see both hello and goodbye message on the screen. This means that memory was automatically freed as soon as the smart pointer went out of scope. So with a smart pointer, we have made our code safer and easier to maintain. No risk of forgetting delete statements anymore. Smart pointers in C++ come in three main types: unique, shared, and weak pointers. Let's begin with unique pointer. A unique pointer gives exclusive ownership of a resource. It means only one unique pointer can point to a particular object at any given time. If you try to copy it, the compiler won't allow it, because copying would mean two owners, which defeats the purpose. Instead, ownership can be moved. In this example, we use a std move to transfer ownership from P1 to P2. Another great feature is that when a unique pointer goes out of scope, it automatically deletes the object it manages. So no need to manually call delete, as I've already explained this. Just note that when we use move to transfer the ownership, the old owner, P1 here, becomes empty, and only the new owner, P2, owns the object. So in practice, unique pointers are perfect for resources that must not be shared, things like files, sockets, or buffers. Next, we have shared pointers. As the name suggests, this one allows multiple owners of the same block of the heap. This type of pointer keeps a reference count. It keeps the number of shared pointer objects currently pointing to the same resource. Each time we copy a shared pointer, the counter increases, and each time one goes out of scope, the counter decreases. The big advantage is that the object is automatically deleted and the heap memory is released when the last shared pointer owning it goes out of scope. This means we can safely share ownership across functions, classes, or different parts of the program without worrying about who deletes the object. For example, here I copied P1 into P2. Now both P1 and P2 share the same object, and the reference count is 2. If one of them goes out of scope, the object still stays alive because the other one still owns it. The heap memory is only released when both P1 and P2 are gone. So shared pointer is really useful when we need shared ownership, for example in graphs, trees, or observer lists. Before we talk about weak pointer, let's look at a common issue, circular references. Suppose we have two nodes A and B. If A points to B with a shared pointer and B points back to A with another shared pointer, then none of their reference counters will ever drop to 0. Even when they go out of a scope, they keep each other alive. This is a memory leak. Making one of them a weak pointer breaks the cycle. Please note the gray arrow from B to A, which means a weak pointer, and the weak pointer definition inside class B. We have seen unique pointer gives sole ownership and shared pointer allows multiple owners. But weak pointer just observes an object without owning it. A weak pointer is like a window into a shared pointer. It can observe the object but doesn't keep it alive because it's not the owner of that object. When we want to actually use that object, we call lock. If the object still exists, we get a valid shared pointer. If not, we get an empty pointer, which avoids accessing a dangling object. In this example, if the object still exists, the returned value stores, which is a shared pointer, stores in S, and we can call a method from class A. So weak pointer is essentially a safe, non-owning observer of a shared pointer managed object. Let's wrap up with a quick summary. We started by reviewing how memory is organized in C++, and we saw that the heap is flexible but also tricky because of memory leaks. Raw pointers give us power, but they also put the burden of cleaning up on us, which is easily to miss. The smart pointers solve this by automatically managing memory. We learned the unique pointer gives exclusive ownership. Shared pointer allows safe shared ownership with reference counting, and weak pointer observes without owning, helping to break circular references. So the key takeaway is that smart pointers make our code safer, cleaner, and easier to maintain. For those eager to dive even deeper into the intricacies of C++ memory management, I highly recommend this book. It is written by Robert Johnson, and it's an excellent resource that will take your understanding to the next level. I hope you have enjoyed this presentation, and happy coding!